Hello, everyone. So I've been given the task to introduce James, Professor James Sparks from the University of Oxford, who has so kindly agreed to come to talk to us, participate on the school. But James has just told me that he prefers some briefer introduction kind of thing. So without any further ado, James Sparks talking about localization on supergravities.
It's on? Ah, okay. Yeah. Thank you very much. Well, firstly, thank you for inviting me to speak this week. It's a great honor to be here. It's a huge pleasure to be back in Brazil for a second time. It's a beautiful country, and it's been a wonderful week so far. So my talk is going to be more of a research talk than the school, but I will try to keep this straightforward, and please do stop and ask me questions as I go along. So this is supergravity. You don't need to know anything about supergravity in order to follow the talk, or I will tell you what you need to know, which is fairly limited as I go along. It's general relativity with some other matter and extra symmetry, but it's basically general relativity. So this is work that I've been doing over the last couple of years with quite a lot of collaborators, including Pietro and Carolina. In addition, Jerome Gauntlet, who's at Imperial College in London, Chris Cousins, who's at Oxford, with me, and then quite a few students have been working on this topic. So my students, Alice Lucia, Tabea Sipa, Jerome's students are Yusheng Zhao and Jaehao Park, and Carolina's student, Davide Muniz, has also been working on this topic. Okay, so we've written quite a few papers, and I'm just going to focus just on four-dimensional supergravity on the simplest example. If you want to hear more, you want to ask me more afterwards or tomorrow, please do. All right, so can you read that at the back okay? Is the font large enough? It's okay? Yeah. All right, so the basic idea of this is that this is a new method, so quite a powerful new method for doing calculations in supergravity. So this is to compute observables and by observables, actually, I'm going to focus on the gravitational free energy, or the on-shell action that Pietro told you about earlier today. You can compute other things too. So in supergravity, so supra. And the key, though, is without solving any equations. So I'll write EOM is equations of motion, but I put in brackets assuming solutions exist. So we're going to be working in GR as we were earlier, and so you have the Einstein equations to solve. Normally you find a solution to the Einstein equation, such as the Schwarzschild solution. Then given the solution, you compute things that you're interested in, such as the area of the event horizon, giving you the entropy, or the on-shell action that we heard about earlier. But usually the first step is you find a solution, and then you plug it into something in order to calculate some observable that you're interested in. And this method bypasses that step, so you don't have to solve any equations of motion as part of this process. You do need to assume that there's a solution. Okay, so that's the gist of it. So I'll just say a few words about motivation and the applications. So why are you interested in this at all? Okay, so the first question you might ask is, well, why supergravity? Why are you interested in that in the first place? And the quick answer is, so supergravity theories in various different dimensions, they are the low energy limit of string theory and M theory. And this is believed to be a good quantum theory of gravity. It's obviously a hugely interesting, intricate theory. And supergravities arise as low energy limits of string theory and M theory in different setups. When supergravity was first invented, people hoped that this would be a quantum theory of gravity, that the divergences in GR that Pietro mentioned right at the start would cancel in supergravity, and that's not the case. So just supergravity by itself is not going to work as a quantum theory of gravity. But once you add the other degrees of freedom in string theory and M theory, it's believed to be, this is believed to be a good quantum theory of gravity. So next is ADS-CFT, which again, Pietro also mentioned. So again, you don't need to know much about that for what follows. So I just want to say a few things. So in ADS-CFT, what we're particularly interested in this topic is precise calculations on both sides. So things you can calculate precisely, precise calculations on both sides. And we'll be able to do that because there will be supersymmetry, so SUSY supersymmetry. And you don't need to know what that is, but it's an extra symmetry that will allow us enough control to be able to calculate both sides of this. So ADS is gravity in spaces that are asymptotically anti-de Sitter space, and CFT is conformal field theory. And ADS-CFT is a conjecture that, so we've seen pictures like this in some of the other talks, so you have gravity here in some bulk of space-time. This will be a manifold of dimension little d plus 1, so md plus 1. And that has some conformal boundary, which will be dimension 1 less, so md is the boundary of md plus 1. And there's a CFT living on this conformal boundary. So the ADS-CFT correspondence says that quantum gravity in spaces that asymptotically look like anti-de Sitter space are equivalent to some conformal field theory on the boundary of space-time itself. So it's a conjecture. There's no general proof of this. It's a strong weak duality. So what that means is that when the classical description of ADS using gravity and ADS using the Einstein equations is valid, the conformal field theory is strongly coupled. And so that's very difficult. It's hard to solve strongly coupled quantum field theories. And vice versa. So when there's a perturbative description of the CFT, that's when quantum gravity effects are very strong. And the reason why you can do calculations on both sides is particularly on the conformal field theory side. In the last decade, there have been new techniques to calculate quantities exactly in superconformal field theories. So when you have supersymmetry, you can do exact calculations in the quantum field theory at arbitrary coupling. So those are new techniques. I won't talk about them. So in some sense, the right-hand side here has become under much better control in the last decade, and you might hope to use that to learn about quantum gravity on the left-hand side, assuming this is true. But I would go further and say you can define quantum gravity using the conformal field theory. You can regard that as a definition. All right, and then finally, I hope by the end I get to black hole entropy so that I make contact with Pietro's talk. So black hole entropy and microstate counting. Is another motivation. So here, the black holes are on the left-hand side, the black hole in ADS that we heard about earlier. And on the right-hand side, the microstate counting is done by some calculation in the CFT. All right, so I hope I get to that at the end. That was an introduction to why I'm interested in the problem. Any questions before we get going? Yeah.
Do we have evidence that there are reasons not to believe this ADS-CFT correspondence? Because it seems to be like an assumption, right?
Yeah, but there's but there are proofs of bits of ADS-CFT. So well, in the case with supersymmetry, some of the work that I'll talk about are examples of that, where it's possible to calculate the two sides independently and show, and it's highly non-trivial mathematically, why the two calculations you do end up agreeing with each other. The other situation that's under very good control are the cases where there's integrability. So they're very special. It's where you have an infinite number of conserved charges, and well, so if you know something about the topic, n equals 4 super Yang-Mills theory and is dual to 2B string theory on ADS5 times S5, this is extremely well understood. So where really both sides can be calculated, but really because they're integrable systems on both sides. So there are proofs of this in certain corners of but it's a vast area, right? So there are lots of superconformal field theories, and did that answer the question? Sort of. All right. So all right. So let's make a start. So well, as I mentioned at the beginning, so we're going to look at supergravity. We don't need to know much about the structure of that. You do need to know, though, just for this equation I'm going to write, is so supergravity is gravity, so there's a metric, and supersymmetry is a symmetry that mixes bosons and fermions. So the metric tensor will have some partner, a fermionic partner, and that's called the gravitino. That's this thing that I've written here. So psi mu, mu is a space-time index, and there's also a spinor index on this, which I've suppressed. I won't write spinor indices, and that's a spin 3/2 thing. So that's called the gravitino, and I'm going to write down its supersymmetry variation. So delta is a variation of that field. So this is SUSY variation of the gravitino. Okay, and in supergravity theories, this always takes the same form. The annoying thing about supergravity is every dimension and every amount of supersymmetry, they all look somewhat different. So you just have to learn all these different theories when you're starting out. But schematically, this equation always looks the same. So the first term is a covariant derivative. So del mu, so it's partial derivative, and then there's a spin connection term. So that's the spin covariant derivative. And then the rest of this equation can look like a mess. If you've got lots of matter fields, this can look quite complicated. But I'm just going to write very schematically flux dotted into gamma matrices with an index mu. So by flux, this could be a form field, it could be a gauge field, it could be scalar fields, whatever fields you have in your theory is sitting in here. They will be contracted into gamma matrices, but it must have a mu index. So I just write it schematically like that. And I'm going to remove that line so I can keep going. And then this is a differential operator, right? That's a derivative. And this acts on the supersymmetry parameter epsilon is a spinor. So we're going to be in 4 dimensions. A spinor is something with 4 indices in 4 dimensions. And this is 0. So you set this to 0. And that's what you mean by a supersymmetric solution in a supergravity theory. So to be supersymmetric means your fields should be invariant under the supersymmetry transformation. So this is one of the equations that you impose for supersymmetry, and it's the important one that I wanted to look at. Okay, so this is an equation you want to impose, and it's quite hard to solve. Actually, at first it kind of looks trivial to solve because, so you want to solve this for epsilon. It kind of looks trivial because this is a first order differential equation and it's linear. So at first it kind of looks trivial that why can't you just trivially write down solutions? The problem is it's an overdetermined equation. So if you just put general fields into this, general metric and other matter fields, there won't be a solution. There will only be a solution if you solve the equations of motion, and there are additional things are true as well. So for example, for a black hole, the mass should be equal to the charge, otherwise there won't be a solution to the equation. So for that reason, it's difficult to find solutions. And so people have introduced various methods for understanding the solutions to this equation. So that's what I'll look at next. So this is DEFN is definition. So it's not obvious that this is a good thing to do, but the first step is to define some bilinear forms. Actually, again, this is one of the longer equations, so I erase that line. All right, so there's a capital psi. It's got mu1 up to mu r space-time indices, and there's a little superscript r, just to remind you that there are r indices. And you take your killing spinor and you conjugate it. So that's, you can just assume this is dagger, so Hermitian conjugate. Then you have gamma matrices. So gamma mu1 up to mu r. These would be 4x4 matrices in 4 dimensions, the Dirac matrices, anti-symmetrized on its indices. Here I've written gamma star, and so in this talk I'll be in even dimension, in fact in dimension 4. And gamma star is the chirality operator, or the identity. So in 4 dimensions, that's usually called gamma 5 is the product of the first four gamma matrices. Or I should also say I will be in Euclidean signature. I've not said that yet, but for the moment, it doesn't matter if this is Lorentzian or Euclidean, but I will eventually be in Euclidean. So this is either 1 or the chirality operator. You can put either and you will get a different form. And then I put the spinner, killing spinner at the end. So all the spinner indices here are contracted. The gamma matrices here are anti-symmetrized over the space-time indices. So this is a differential form of degree r on the left-hand side. Okay, so it's just a definition. It's called bilinear because it's bilinear in epsilon, the spinner. And as I said, it's a differential form. And so it's a fact. And this, it goes by the name of G structures in the literature. It doesn't matter what that is, but that's the word that's associated to this. So it's a fact that, so imposing supersymmetry, imposing that you have a solution to this equation up here, is equivalent to some differential and algebraic equations on those forms. For the bilinears. So it should be clear why. So that equation there is a first order differential equation for epsilon. And so if you hit this form with a derivative, you'll pick up derivatives of the epsilon here and the epsilon there, and this will satisfy some first order equation as well. And the reason why this is a good thing is that then you can use geometric methods to solve the equation. Once you express things in terms of forms, now you have the Riemannian differential geometry of forms, or Lorentzian geometry of forms, where people have worked out theories of that over the last century or so. And so you can make use of various geometric methods to solve the equations. So what we're doing really is kind of an extension of that. So here's another definition. So there's a particular form that's important for the talk. And I will raise its index, so its indices are up rather than down, and it's the vector that you construct. So psi will be so psi 1 mu d by d mu. Okay, so you take this thing here with little r is 1, so there's just one gamma mu index. I've raised it with the metric, and then that's a d by d x mu, that's a vector field. Then again, you can check, or you can believe me, that so imposing supersymmetry, so imposing that equation on the left, implies that this psi is a killing vector. So, i.e., the Lie derivative along psi of the metric is 0. So Lie derivative of g mu nu along psi is 0. And moreover, you can actually show it generates a symmetry of the whole solution. So if you have other fields, so remember I said all the other bosonic fields that I have, for differential forms or scalar fields, I just called them fluxes. you can check that these are also invariant. So this psi generates a symmetry of the solution. So that's a calculation to do, but you can check that it's true. And so I just want to remark before I introduce another idea, is that this is very general, what I'm saying. So everything that I've said so far, this could be any gauged or ungauged, if you know what that means. It could be any supergravity theory coupled to matter, any matter. But it also applies to internal spaces in string theory and M theory. So this is where I apply everything that I've just said to the internal space of a compactification rather than to a supergravity theory. That also has exactly the same structure. But I won't talk about that at all. Okay, so it's incredibly general so far. So I just have to make one more definition. So far we've now got two things. We have a whole bunch of differential forms that are natural to introduce. And there's also a vector field. It's a killing vector, and it generates a symmetry of the problem. So if you're mathematically inclined, you'll know that there's a natural operator that you can introduce in this setup. So this is d subscript psi, and it's d, where this is the exterior derivative. So exterior derivative acts on a p form and gives you a p+1 form. But then you subtract the contraction with the vector field. So this hook thing means you contract the index of your vector field. That's got a mu index up. You contract it into an index of your p-form field, which has its index down. And so this raises the degree of the form by 1, and this reduces it by 1. It's called equivariant exterior derivative. It naturally acts on, therefore, on multiple degree forms, because if you start with a 2 form, say, this is going to give you a 3 form, and that's going to give you a 1 form, so it mixes the degrees. So it acts on multiforms, and if you square it, you get minus the Lie derivative. This is sometimes called the Cartan formula for the Lie derivative, acting on forms. And I just told you that the Lie derivative of everything here is 0. So this is a nice operator that squares to 0 on the forms. So again, if you're a mathematician, if you find an operator that squares to 0, it's nilpotent. There's immediately lots of structure that you can employ. All right, so those are the ingredients that we need. The new idea in supergravity is to construct, so it'll be multi-forms. So forms of mixed degree, phi, capital Phi. They're going to be polynomial in the bilinears. So polynomial in these forms that I introduced here. And also the supergravity fields. where when you impose supersymmetry, so the equation that I just removed, the killing spinor equation, then those forms are closed under this operator. So when you want to construct forms which are closed under that operator that squares to 0. All right, so I'll make a few remarks and then I'll ask if there are any questions. So one is there are typically lots of these in a given theory. So as I said, you can, everything I've said is very general about supergravity. You can apply this to different theories, and you will be able to construct lots of these forms phi that satisfy this equation. So we have done that in lots of cases. The second point is that actually you only need a subset of all of the equations in order for this equation to be true. And in that sense, the results that I'm going to tell you, they hold partially off shell. So you don't actually need to impose all the equations of motion in order for that to hold. That won't be particularly relevant for the talk today, but in other situations it is relevant. And so thirdly, the most important thing and what's most surprising is that many physical quantities may be computed as integrals of these forms using a fixed point theorem. So I'm going to tell you about that next. Without solving any equations. And so nothing I've told you guarantees that to be true. So in practice, what we found is you take a theory, you search for these forms capital phi, which satisfy this condition. Great. If you find one and you integrate it, it's always something physically interesting. So I will focus on the on-shell action for this talk, but there are many other quantities you can calculate this way. So that's first of all, so they're always physically interesting when you find these. And secondly, because of this property that they're related to a nilpotent operator, I can then apply some mathematics, the fixed point theorem, in order to calculate the integral. And lastly, you don't have to solve any equations of motion in order to obtain explicit expressions, and that's not obvious from what I've told you either, but it's nevertheless true. All right, any questions? Yeah, lots of questions. You have Poincare lemma holds also for this derivative, but I'll be using a global fixed point theorem. In fact, I'm going to tell you about that next. Well, and this equation should hold everywhere, right? So you want your solution to satisfy this. It's supposed to be supersymmetric solution, so it should satisfy this condition everywhere. Oh, it's no and no, exactly, no. That's right. Otherwise it would be, its integral would be 0, yeah.
You said that like there are some values for the theory that you cannot solve the equation analytically. Can they still be solved computationally in a reasonable time?
Yeah, so, yeah, that's a good question. So, if I get to the black holes at the end, these are good examples of where this will allow you to calculate the on-shell action, the free energy for the black holes. And in general, we can only solve the equations for the black holes numerically. So without this technology, it's very hard, and not just very hard, but I think it would be impossible to calculate these things. So that's what this gains for you. Most solution to the Einstein equations, you cannot write analytic solutions. You have to do it numerically. This will just give you the general answer. All right. Good. So maybe I switch to the top boards because it's a change of topic. So I'm going to tell you a little bit about localization. And that's the theory of this operator here. So this operator was, it's a very natural, simple thing to write down, but it wasn't written down until 1982, which is kind of surprisingly late. I mean, exterior derivative has been around for more than a century, much longer. And this is a very natural thing to write down. It was introduced by Witten in his paper on supersymmetry and Morse theory in '82. And then independently, Berlin and Verne, two mathematicians, also introduced it. And I'm going to tell you a little bit about that topic. Okay, so this is interlude. So this will be localization in 4 dimensions. So capital D is the dimension of space-time, is 4. So the ingredients are, so forget physics, we're just going to do some geometry. So you have a 4 manifold, M4. It doesn't have to have a metric, just a 4 manifold. And a vector field, psi. And we're going to have a multi-degree form. So capital Phi. And I'm going to take it to have a 4-form piece, Phi 4, a 2-form piece, Phi 2, and a 0-form piece, Phi 0. So this is a function. Phi 0 is just a function. And this will be, suppose that it satisfies, or satisfying, that it's closed under this operator that I erased. D psi of phi is 0. So if you write out what does that equation mean, it means if you contract psi into phi 4, it's d of phi 2. So contracting the vector into a 4 form is a 3 form. That should be d of the 2 form. And if you contract psi into the 2 form, that should be d of the function phi 0. So if you just write out what that is, so write it out. This is completely equivalent to that equation. And by fixed points, I mean where the vector field is 0. So it's a fixed point in the sense that when you have a vector field, that's a little arrow pointing pointing in a direction at each point. It generates a group action where you just follow the orbit of the vector field. So that generates an infinitesimal group action on your manifold. And then the fixed points are where the vector field is 0. So your arrow is 0 there, you don't move anywhere. In that sense, they're fixed. So in 4 dimensions, there are 2 types of fixed points that you can have. They're either isolated points, and this topic goes back to a paper, I should have said at the beginning perhaps, there's a paper by Gibbons and Hawking from 1979 where they looked at some of what I've told you in pure gravity, not with equivariant forms. So those hadn't been invented yet because that was 82 and there they were in 79. Anyway, they call isolated fixed points, they called them nuts after the Taub-Nut solution. So it was a bit of a, bit of a joke. Anyway, they called them nuts. So locally, at an isolated fixed point, your vector field must look like the following. So it'll be B1 d by d phi 1 plus B2 d by d phi 2, where d by d phi 1, let me write d by d phi I, rotate the tangent space R4. So we're at a point in a 4 manifold. Its tangent space, it look locally like R4. And what we're saying is that the R4 is naturally going to be R2 plus another copy of R2. So I labeled them by 1 and 2. And the 2 vector fields, d by d phi 1 and d by d phi 2, they just rotate those 2 copies of R2. So you have a plane, there's a vector field that rotates the plane. And the rate of rotation of the first plane is B1, and the rate of rotation of the second plane is B2. So the statement is you can always choose coordinates so that your vector field will look like that, near to the point. So rotating the 2 planes with some weights, B1 and B2. Okay, so they're either isolated fixed points like that, so where the point is the origin of R4, or they're fixed surfaces. And Gibbons and Hawking called those bolts. Again, that was supposed to be a joke, because if you have a nut, the other one must be a bolt. Okay, so if you have a fixed surface in 4 dimensions, it will be a Riemann surface. So it's 2-dimensional surface. So it'll be some Riemann surface sigma g of genus G. They appeared in one of the mini courses this week. And in this case, you can write your vector field psi as B times d by d phi, where the d by d phi rotates the normal direction. Okay, so you've got, remember, in 4 dimensions, and you have a surface. The directions normal to the surface, those are that's a 2-dimensional space, and d by d phi rotates that space. So to make contact with what Pietro was talking about, little b here, the weight of this vector field, that's surface gravity. It's exactly the same thing. So that's what Pietro called kappa, I'm being more of a mathematician, it's a weight of the vector field. It's exactly the same thing, where my Riemann surface here would be the horizon, and then this vector field would be rotating the Euclidean time direction normal to the horizon. Okay, is that all right so far? Great. All right, so you can have arbitrarily complicated four manifolds, and this could be quite a complicated set. So given that setup, there's the fixed point formula we're going to use is called the Berlin-Verne-Atiyah-Bott formula. So they're all mathematicians, and this was proved in 82 or 83. It's a formula for the integral. So you want to integrate phi over your four manifold. By definition, that means you integrate the four-form part. Okay, it doesn't make sense to integrate a function over a manifold or a two-form over a four manifold. So by definition, this means we integrate the four-form part, the thing you can naturally integrate. And the formula says the integral is given by something that you evaluate just at the fixed points of the vector. In that sense, it's localizing. So the only contribution to the integral that you have is the fixed points. That's what the word localization is supposed to mean. So it's quite a simple formula. So you sum over all the nuts, the isolated points. It's 2 pi squared. And then there's B1, B2 is the product of the two weights here. And phi naught is the value of the function at that fixed point, at the nut. And then you sum over the bolts, the fixed surfaces. You have 2 pi divided by b. So b is the weight, or it's the surface gravity. And then there's an integral of the bolts. So the bolts are two-dimensional, so I have to integrate two forms. So phi 2 appears here, then minus 2 pi over little b, that's the weight. And then there's a topological term, again, so we don't really need it, but I put it for completeness. So this is C1 of L, and then that's phi naught. So where L is the normal bundle to the bolt. And this is called first Chern class. So this is some topological invariant. We don't need to know what it is, but it's a topological term that enters the formula. But you can ignore that. Okay, so the formula just relates the integral over the manifold to some integral and sum over the fixed points. It doesn't look like this necessarily gets you very far, right? You want to calculate that, and this expresses it in terms of some other quantities. It's not clear that this is helpful, but it will be when we get to supergravity. Okay, and I'll do a baby example. So it's all been fairly abstract so far. So I'm going to do an example in 2 dimensions of this formula. So here I was doing 4 manifolds. You can do this in any dimension, even dimension. I'm going to do it with a 2-sphere. So M2 will be a 2-sphere in spherical polar coordinates. My vector field, I will take it to be little b times d by d phi. the obvious rotation of the two-sphere, where you rotate it around the equator. So here's a two-sphere. My vector field is just rotating it around the equatorial plane. And so it will have two fixed points at the north pole, N, and the south pole of the sphere, S. So it fixes theta equals naught in polar coordinates and theta equals pi. So that's the north pole and the south pole. Okay, and then I have to pick, I need an equivalently closed form. So this will be a sum of a 2 form, phi 2, and a 0 form, phi 0. And for the 2 form, I take just the usual volume form on the sphere. So sine theta, d theta, d phi is the usual area element for, or volume form for a 2-sphere. And then I add b cos theta. So that's the 0 form part of the function. And you can probably just see by inspection that that satisfies d psi phi is 0. So the contraction of psi into this is d of that. It's basically just you use d of cos theta is minus sine theta. That's it. Okay, so the volume of the 2-sphere is the integral over m2 of phi. And the fixed point theorem tells you that that integral is given by a sum of contributions, one from the North Pole and one from the South Pole. So you get 2 pi divided by, so you can see in these formulas you divide by the weight, so you get 2 pi divided by b times phi naught at the North Pole, which is theta equals naught, plus 2 pi divided by minus b phi naught at the South Pole, so evaluated at theta equals pi. And there's a minus sign because if you imagine you look at the North Pole of the sphere and your vector field is going anti-clockwise, then if you look at the South Pole of the sphere, that same vector is going clockwise. It goes in the opposite direction. Hence the minus sign that you get there. Okay, so you can plug, so here's phi naught, so you need to evaluate cos theta at 0 and pi. And if you put this in, you just get 4 pi. The factors of b cancel. You get 2 pi minus 2 pi, which is 4 pi. So this is a particularly stupid way of calculating the volume of a sphere, but it's the simplest example that you can give of the fixed point theorem. Yes. Well, you need d of this to be the contraction of psi into that. So, yes. Yes, although on a sphere it's particularly simple to do that anyway. So, because you can just use Stokes' theorem. In fact, really, this It has fancy name, this formula, but it's Stokes' theorem. If you had maybe an hour's lecture, you could prove it. So it's essentially you prove it using Stokes' theorem, and it's just a slightly fancy version of Stokes' theorem. And that's really what's going on here. I mean, you know that sine theta is a total derivative. You write it as d of cos theta. That's all that I'm doing. I'm just expressing it in a more fancy way. Yeah, so for the two-sphere, this is not at all interesting. But the example I will now, applying to supergravity, it's much more interesting. Well, I hope to convince you it's more interesting. All right. So that was a little interlude on equivariant forms, localization. All right, so then we go back to supergravity. I will be in Euclidean signature, so it's Euclidean, for the reasons that Pietro explained to us earlier. I'll be in 4 dimensions, and this will be, it's called n equals 2 gauged supergravity, but you don't need to know what any of that means. It's just Einstein-Maxwell theory. So that is, it's just going to be GR with a abelian gauge field, a Maxwell field. And the thing I'm going to want to compute is the on-shell action, exactly as Pietro was doing this morning. All right, so I write, you never wrote my handwriting is quite large on the board, so I'll see if I can get it on this line. So this we saw earlier today. So capital I will be the on-shell action, so you take a solution of Einstein-Maxwell theory and you plug it back into the action. There's a minus 1 over 16 pi g, where I will keep the Newton constant. Then there's an integral over M4, and then here we have the action, the bulk action. So the Ricci scalar plus 6 minus f squared. So this is the Ricci scalar, little g because there's a bulk metric and there's a boundary metric. So little g is the bulk metric. 6 is because I've put the cosmological constant to minus 3. You can do that. You don't have to, but I've set that to minus 3. And then f squared, f is the Maxwell field strength. So Maxwell, f is dA. So f is a 2 form, a is a 1 form. And f squared is f mu nu. F mu nu is the kinetic energy in Maxwell theory. So it's exactly as Pietro had with a Maxwell field. Then there's a boundary integral, which is the Gibbons-Hawking-York term. So that's 2 times capital K, the extrinsic curvature trace. And then you have the volume, the volume element, but with respect to the boundary metric, which Pietro called little h earlier. That's the volume form for the bulk metric G. So that's a 4 form, that's a 3 form. And then there are the counter terms. So there are also boundary integrals, and it's 4 plus the Ricci scalar of the boundary, so r of little h integrated over the boundary. Okay, so we had literally that this morning. There's an extra Maxwell field, otherwise it was the same as we had earlier. Okay, then the next step, if you remember, there were bilinear forms. So where you take the spinor, the killing spinor, and you construct some differential forms, and there are a few of them. So there's S is epsilon dagger epsilon. That's a scalar. So the spinor indices are contracted. That's a scalar, so it's a function. And P will be the same thing where you put a gamma 5 in the middle. So those are both scalar functions. So they're scalars or functions. There's the R symmetry killing vector. So you have a one form, you raise its index, it gives you a vector field. This is minus I epsilon bar gamma mu gamma 5 epsilon. And there's an I here just so this is real. If you don't put the I, it's not real. That's a real vector field. And finally, there's a two form that's relevant. So mu nu is defined as I epsilon bar gamma mu nu epsilon. So it's got two indices, mu and nu, it's anti-symmetric, so that's a two form. Okay, so those are the relevant bilinears. You can construct others, but I don't need them. Then this is the form that I'm interested in. So it's 3 times the volume form, that's a 4 form, plus f wedge star of f. So the star is the Hodge-Joule operator. It takes a 2 form into a 2 form. So that's a 4 form, and it's, well, if you integrate it, that's the kinetic term for Maxwell. So that's a 4 form. Next, I add a 2 form. So U plus S times F minus P times star of F. So F is a 2 form. If I multiply it by S, that's a function. So this is a 2 form. And then similarly, this is another 2 form. And finally, the function component is minus S times P. It's a product of 2 functions, so it's a function. So this will be, in the notation earlier, that's phi 4. This is phi 2. And that's phi 0. Okay, and then so all of that's just definition. There's just one calculation to do, which is you check that supersymmetry of this theory, which I've not written down what the equation is, but there's a precise form of the equation I started with. That gives you some differential equation for epsilon. It's a calculation. You check that that implies that this form I just wrote is closed under the equivariant exterior derivative. Okay, so I'm certainly not doing that, but in principle it's not a difficult calculation to show. Great, so now I'm good because I've got an equivariantly closed form. And I know I have a theorem that tells me how to integrate it. And what's interesting about it is that the 4 form piece here, when you integrate that, it's exactly this term here evaluated on shell. Well, I'll write a formula in a minute. When you solve the Einstein equations, you can substitute the trace of the Ricci tensor, the Ricci scalar, in favor of the other 2 terms using the Einstein equation, which is why there's no Ricci scalar term here. I've eliminated it using the equation of motion. All right, so just to write a formula, I, the on-shell action, so the thing up there, is 1 over 2 pi squared, integral over m4 of phi. So remember that means you integrate the 4 form piece on the left. Then you get pi over 2 times the Newton constant plus boundary terms. Okay, so all the stuff here on the boundary, the Gibbons-Hawking, I just called it boundary terms. Okay, and in the next line, I tell you what it is. So this, in the next line, I apply the fixed point formula. So it's a sum over the nuts, so the isolated fixed points, where the vector field is 0. And they're going to get a little label. They're going to get a plus-minus label. And I say what the plus-minus is in a minute. Then minus plus b1 minus plus b2 squared over 4b1 b2. I remind you, b1 and b2, they long since got erased. b1 and b2, they're the weights of the vector field at the nut. That's it for the nuts. And then there's a sum over the bolts. So fixed surfaces. They come with a label plus minus. And remember we said they're Riemann surfaces. So it's a two-dimensional thing inside a four-dimensional thing. Two-dimensional things are Riemann surfaces. And it's 1 minus the genus of the surface. So how many holes it has is the genus. Then there's minus plus a topological invariant, which again, you don't need to know what it is. So this thing, sigma g dot sigma g, is called self-intersection number. It's a topological invariant of the surface embedded inside the four manifold. It's an integer. But you don't need to know what it is, but just to give the general formula. So it's some integer that's a topological invariant, and that's it. Pi over 2g. Yeah. So okay. Let's note a few things. So firstly, at a fixed point, you can show that necessarily the spinor is chiral there. So gamma 5 on epsilon must be plus or minus epsilon. So this is called chirality of spinors. If you've done anything with spinors before with gamma 5, so spinors satisfying this are usually called Weyl spinors in 2 dimensions, and you can then write them as 2-component things rather than 4-component things. Anyway, so the spinor must satisfy this. That's called being chiral. So gamma 5 squares to 1, right? So it has eigenvalues plus minus 1. And you must be in an eigenstate of that. And it means that these scalars that I had, P and S, P is plus minus S. If you look at the definition up there, it means that P and S are equal up to sign. So that's what all of these plus minus signs are in the formula. The other remarkable thing is that the boundary terms have all gone away. They cancel. So I call these UV terms. This is ADS-CFT language, but all the boundary terms at infinity in space-time, they cancel. And finally, the formula is general. It's a completely general formula, and it's almost entirely topological. So it's really surprising that this is true. I think I don't understand, still quite know why this is such a strong formula is true. This is any supersymmetric solution to Einstein-Maxwell theory. This is a formula for its on-shell action. It assumes nothing else than what I just said. So all we used was supersymmetry, nothing more. The contribution from isolated fixed points, you just need to know the weights of the vector field at the fixed point. And the bolt, this is entirely a topological invariance. You have the genus of the surface, it's an integer, and this self-intersection number is also an integer, and that's the general formula. So to go back to the picture I had earlier in terms of ADS-CFT, you have a bulk space-time, M4, and so sitting inside here are the fixed things. So there's some, that's supposed to be a fixed Riemann surface there. There may be some various nuts, some isolated fixed points in orange. And it has a boundary, conformal boundary, over here. The on-shell action just receives contributions, and they're almost entirely topological from the fixed points. And in the strongly coupled limit in ADS-CFT, so this is, usually it's a large n limit, so where n is the rank of a gauge group, but this is in the strongly coupled limit, this gravity on-shell action that I've calculated is, as Pietro had this morning, minus log of the partition function. So it's a beautiful thing. You calculate, your field theory lives on this boundary here. You calculate the partition function. This is something that you can do exactly with these methods that I mentioned at the start that have been developed in the last decade. So you can calculate this exactly at all couplings. And this formula tells you that that receives contributions just from these fixed points in the manifold. So it's kind of a remarkable piece of mathematics that that's true. And you can look at examples and see that it is true. I think we still don't understand deeply mathematically why they give the same answer. But in any case, this was the motivation for looking at this topic in the first place. All right, I don't have too long, but I'll tell you a little bit about black holes. Any questions before I do that in the last 10 minutes, 15? All right. So that was supposed to be kind of example one, was Einstein-Maxwell theory. Example two, now we introduce some matter, some other matter fields, so coupling to matter and Euclidean black holes. So as I said at the beginning, there are lots of different supergravity theories that people have looked at. The one I'm going to look at is called the STU model. The reason that it's interesting is this particular supergravity is related to M theory. But otherwise, it's not important. But that's why we're looking at this particular theory. So I tell you a little bit about it. So it has 4 Maxwell fields. So we were looking at a theory with 1. Now there are 4. So capital I runs from 1 up to 4, labels the Maxwell fields. There are 4 scalar fields. Which will be called capital Xi. So again, I runs from 1 to 4. If you know anything about supersymmetry, these live in the same multiplet. So the fact that there are same number of these as these is because they live in some particular multiplet. So that had to be the case. And the only other thing we need to know about the theory is its entire Lagrangian is determined by one function, which is called the prepotential. I'm not going to write the Lagrangian because it's not that attractive. So, Lagrangians have got potentials for scalar fields. This is called a prepotential because if you know that, you can work out the potential. You can work out everything, the whole Lagrangian. And it's also quite a simple function. So it's a function of the scalars. So it's curly f. It's a function of xi. It's 2 times the square root of the product of the scalars. So x1, x2, x3, x4. So don't confuse these with powers. The indices are up for historical or supergravity notational reasons. That's 4 different scalars multiplied together. Okay, so I haven't told you much, but that's the field content of the theory. And as I said, I won't write down the Lagrangian and action and so on. It's complicated. But I'm going to look at black holes in that theory. And in Euclidean signature. And as we heard earlier today, the black hole looks like R2 times the horizon. So Pietro had a 2-sphere for the horizon earlier. This will be a general genus G Riemann surface for me. So that's the horizon of the black hole. I mean, you can say that you shouldn't call that a black hole if it doesn't have a 2-sphere horizon, but I call them black holes. And the R2 direction is rotated by the Euclidean time direction. So the vector field, the R symmetry vector field psi, the one in my localization, will rotate the Euclidean time direction, rotates R2. You called this TE earlier, but people also call it tau, is Euclidean time. So that's Euclidean time. And the only one other ingredient is, in general, these can have magnetic charges. They have electric charges as well, but they don't enter the formula. So the magnetic charge is pi, and it's what you get by integrating 1 over 4 pi, the volume of the 2-sphere. And then you integrate Fi, so that's the Maxwell field I, and you integrate it over the horizon, sigma g. So that's the flux, the magnetic flux of the gauge field through the horizon. You call that the magnetic charge. Okay, so that's what we're going to look at. So they're like the black holes that we had this morning, but they have some more matter. There's a localization formula for the on-shell action for this theory, which I won't write down, but I'll just write down what the formula gives you for these black holes. You see, you might have thought it was an accident that in Einstein-Maxwell theory we had this nice formula for the on-shell action. You might say, well, that's nice, but probably it doesn't work in other cases. It's not true. So in all the cases that we look at, there's always a beautiful formula like this. In particular, there's one that has a dependence on the pre-potential, and there's a general formula for it. So the fixed point set here is the horizon, and so our localization formula just allows us to write down the on-shell action. It's more precisely, it's the gravitational free energy, which is not quite the same thing, but I'm going to suppress that. This is essentially the on-shell action that I'm writing. And I call it gravitational free energy. So our formula just allows us to write down the answer. So it's the pre-potential. Now the variable is this little u, and I write what that is in a moment. So product of 4 u's. And I have a sum from I is 1 to 4. There's the magnetic charge, pi, divided by ui, times pi over 2g. So the formula, our fixed point formula just allows us to write down the on-shell action for these black holes. And the only thing you don't know is what is u. So ui is xi divided by the sum of xj. J is 1 to 4. Evaluated on the horizon. So the fact that you have this sum in the denominator, this now depends on the structure of the theory that I've not told you about. That's where it comes from. But so this is just a scalar, right? The x is a scalar fields. This is just some combination of scalar fields, and I call it u, and that's the thing that enters the formula. So they're scalar fields, and you evaluate them on the horizon. And then that's the answer. So to go back to the question that we had earlier, these are solutions where the general solution is only known numerically. So there are some examples for particular magnetic charges. There are analytic solutions. For the general case, there's no analytic solution. And the people that first found these black holes, they found them numerically, by numerically solving the Einstein equations. But the beauty is the formula we have just allows you to write down the answer. You don't have to calculate anything. And this agrees with their formula that they had after 70 or 80 pages or something that reproduces the answer. Okay, so that's already nice, but this is not quite good enough for ADS-CFT, and in particular you can say, okay, so to evaluate this, you need to know the magnetic charge. Okay, that's a conserved quantity. You need to say what the magnetic charge of your black hole is. But how do I know what these scalars are on the horizon? I don't know what that is. So in that sense, I don't know. How do you evaluate that? So we prove another formula. That relates the quantities on the horizon to quantities on the conformal boundary. So this is capital delta I plus little I, square root of -1, beta, sigma I. I just need to tell you what all those things are. So delta I is 1 over 4 pi, and then you integrate around the circle. So the Euclidean time circle, you integrate the gauge field AI. Beta is beta from this morning's talk. It's the period of the Euclidean time circle. So delta tau is beta. And finally, sigma is chemical potential. I think Pietro generally called these phi in his formula earlier. It's not exactly phi, it's dressed by some other things, but it's essentially the chemical potential. And so the important point about that formula is the left-hand side is on the horizon of the black hole, and the right-hand side is on the conformal boundary. And again, we prove that formula using fixed point formula, the localization again. Okay, so here's the cartoon. This is what the space-time looks like. There's a horizon of the black hole, so some Riemann surface over here. And over this side, I draw the conformal boundary. So it has a circle. So the circle is the boundary of R2. That's the Euclidean time circle, so S1 tau. And the boundary of the space-time is S1 times sigma g. So again, Pietro had S1 times S2 earlier, and here my horizon is sigma g, so it's S1 times sigma g. And so this gives us a formula for the gravitational free energy, so the on-shell action, in terms of quantities that are just on the boundary here, on the conformal boundary. So U is delta plus I beta sigma is a function of things that you just measure on the boundary, so boundary variables. Okay, so I'm a couple of minutes over, but I write one more formula and then I'm done. So the punchline of this is that you can exactly compute. So it says that the motivation for this was ADS-CFT, and the fact that in field theory you can calculate the partition function, for example, exactly in field theory. So you can exactly compute, so people have exactly computed the logarithm of the field theory partition function in this case. So you're doing the partition function on S1 times sigma g, and it's I have supersymmetry, so it's a superconformal field theory that's called the ABJM theory, but it doesn't matter, it's some specific field theory. You can calculate the partition function exactly, and people found exactly the same formula. So 2 square root U1, this is the product of 4 U's. So these U's here, it's exactly the same formula that I've got there. So Pi over Ui, and then the free energy on the 3-sphere, which is pi over 2g, which I think Pietro told you earlier was a fun exercise to calculate the free energy on the 3-sphere. That's why pi over 2g has been everywhere. It naturally appears as the free energy on the 3-sphere. And this is in some strongly coupled limit, in a large n limit. I'm not telling you what that is, but it's a strong coupling limit. And then this is an example of precise calculations you can do in ADS CFT, where the CFT side is exactly computable, and so is the gravity side. So this is one of the simplest examples that you can do, but we've been looking at more interesting things over the last couple of years. I think the hope with this whole program is to learn about the quantum gravity path integral that Pietro was telling you about earlier, because in this setup, as I said, the field theory side of this is exactly computable. And so this is really telling you, so I've only done a large n limit here of that answer in order to compare to classical or semi-classical gravity. If you could quantize gravity, you should get the exact answer here, which is known. So this is telling us about quantum gravity, and we should be able to learn from this using the localization that we've introduced. Or at least that's the hope for this program. I will stop there. Thank you.
All right, thanks, James, for the talk. Great talk. Questions?
So my question is not directly associated to supergravity, but to supersymmetries. Can you have anomalies associated to supersymmetries?
No, not in 4 dimensions. You can in odd dimensions. That's quite a different story. It's a very good question. I mean, so the general answer is yes, you can, but not in even dimensions.
Okay.
Yeah, in even dimensions, you're generally speaking safe from anomalies. Even bulk dimensions, there are no anomalies. But it's a very different story in odd dimensions. So if you try to repeat this in 5 dimensions, which we did recently, there are lots of issues. So one of them is, well, let me not go into all of the issues, but anomalies, including anomaly and supersymmetry, are all very much there, and they just complicate the story that I'm telling you.
Is this generalities of any supergravity theory due to the high supersymmetry that's happening, or the internal holonomy?
Sorry, I didn't...
Like you have generalities for any supergravity theory, as you said.
Yes.
Is that because of the high precision, the high supersymmetry that you have, the number of supersymmetries, or the internal structure of the holonomy, I mean?
So I think in order to do what we're doing, you need 4 supercharges or more. You have that automatically above 4 dimensions. Yeah, so probably you can do what we've done here with less supersymmetry even in 4 dimensions, but I don't know that for sure. I think that's potentially true. Yeah, I think one of the issues with this topic is the structure of all of this looks different for each theory. So it's a lot of work. So you need to sit down with your particular theory, and you can then apply the formalism that I've described, but it's different in each theory and in each dimension. And so it's just somewhat how supergravity is. It's hard to do all supergravities in one go because they have quite different structures. But I think that's what's surprising, is that this structure is there in all of them. It looks, the expressions for the forms and so on is different because the matter is different. But nevertheless, these equivalently closed forms are there. The way that these calculations go, it goes exactly the same in all cases.
And the construction for even dimension is because of the topology of Dirac operators. Like, I mean, you are using a Thiele-Singer theorem implicitly, so this is why you just have for even dimension, or
yes, Yes, but you can still do things in odd dimensions. It's just the story is slightly different. You don't have isolated. There's still fixed point theorems in odd dimensions, but it's more complicated.
This is probably a very naive question because I'm not from the field, but I'd like to understand where singularities of black holes are in this program. Are they there?
Yeah, they're not in the Euclidean, yes. So, yeah, if you remember, well, this could have been a question for this morning. So the horizon was at some radius r plus, and the singularity of the black hole is inside the horizon. So it's for r smaller than r plus, where it's at r equals 0. But when you go to Euclidean signature, the space-time caps off at the horizon. So it's, I wrote quite big, so everything got deleted. But the space-time is, here was r2 times sigma. The origin of r2 is where the horizon is. That's r equals r plus, and that's the horizon at the origin. But that's it, the space is now closed off, so you lose the singularity from the solution completely in Euclidean signature. It's not there anymore.
And something else, a curiosity, just to pick your brains on something. LIGO-Virgo collaboration have just shown that the Hawking area theorem applies to the merger of two black holes. What does this tell concerning what you've just presented?
Probably not much. So that's a very dynamical situation. So here, this supersymmetric situation, there is always a killing vector, I told you. And for solutions which are black holes, it's the obvious killing vector associated to time translation for static black holes, but that makes them at least stationary. They have a killing vector. So dynamical things like this is not going to tell you anything about it. It could tell you about end states, which are stationary or approximately stationary, but not about the process itself, which is what you're asking. So at least I don't see a way to say anything immediately. Yeah.
All right, so James still here tomorrow. If you want to talk to him, I'm sure he'll be delighted to talk to you during coffee breaks or perhaps the poster session. So I'll leave it at that. Let's thank the speaker again.
Okay, thank you.